Greetings wherever and whenever you are. My name is Tom and I'm here to talk to you about biodiversity. I will be introducing the science surrounding biodiversity, including the definitions, the patterns, its measurements, the processes driving biodiversity, and the value of biodiversity. Biodiversity was coined relatively recently in the 1980s. It was called biological diversity first, but after the World Summit in 1992, the term became far more common in the public zeitgeist. The simplest term for biodiversity is the number of species in a given area, but the Convention for Biological Diversity in 1992, which is international legislation to address loss of species worldwide, they had to define it, and the definition they provided was the variability among living organisms from all sources, including inter alia, terrestrial, marine, and other aquatic ecosystems, and the ecological complexities of which they are part. This includes diversity within species, between species, and of ecosystems. Of all the species known across the world, 1.2 million species have been described, but it is thought that there are 7.5 million species still to be described. The majority are invertebrates, with beetles particularly speciose at 360,000 species, in which it may have been said that a creator would have had an inordinate fondness for beetles. There were so many species in relation to other species. And there are more beetles than there are plant species described. By comparison, there are not as many vertebrates, chordates described, of which there's not even 5,500 species of mammal. Looking at this infographic hits home the message. This fly represents all the insects. In proportion to the number of species of mollusks, of arachnids, these are scorpions, mites, spiders, to plants, to birds, of which there's about 9,000 species. There's the fish over here, of which there's 31,000 species. And you do struggle to find where the mammals are, but here the mammals are by comparison. It just shows the distribution of species across the world. And see if you can find a species or an animal group you like, or that you can compare that to. Across the globe, this is concentrated often in the tropics, between the Tropic of Cancer, Tropic of Capricorn. The Amazon basin is particularly rich in species, and as are the rest of the tropics, especially Southeast Asia, and with notable absence of species, or not as many species, in the polar and boreal regions down here. But this previous map does not take into account endemic species and densities of unique endemic species, which are unique species. These are often accumulated in mountain ranges, such as in the Andes, in Africa, such as around Cameroon or Tanzania, and also in the Western Ghats in India. But then there are islands, such as in Southeast Asia and in Madagascar, with all the lemurs, and also the Galapagos Islands, where you may be familiar with all those giant tortoises and flightless cormorants and unique penguins and marine iguanas. So that just as one example. But it's important on how you measure biodiversity. First, you need to describe your species, and it's good to understand what the biological species definition is. And again, you'd do that in a natural history museum first, but once you got that sorted, you then look at species richness to start with, how many species are present. But then again, it is important to understand the scales, such as alpha, beta, and gamma scales, which are roughly speaking, the local, regional, and global scales, respectively. It's important to take abundance of each species into account if you can. So this then takes evenness into account, which then relays into indices of diversity, such as Simpson's index and Shannon index, which will be useful to look at later. but species identity itself is useful. It's increasingly good to be important, such as looking at traits such as is it carnivores versus grazers. And then there's evolutionary distinctiveness, and do check out the ZSL Edge of Extinction program, and we can talk about lineage length, such as with these echidnas versus these rodents. Obviously, biodiversity is created through evolution, it's created through opportunity. So availability of resources, say in tropical areas where if you have sun all year round, you have solar radiation all year round, which creates a lot of resources through photosynthesis, which other consumers can take and cascade up the food web. The stability of that environment is also important. Like there's no ice ages to push things out. There's structural heterogeneity. So, say in if you compare a rainforest to a grassland, you'll see there's lots of vertical strata. So there's lots of places for different species to live vertically as well as on the horizontal plane. And there's also spatial heterogeneity, such as mountains and oceans and islands, and also connectivity, because islands have fewer species compared to mainlands, and all that's linked to isolation and opportunities for evolution, for lineages to accumulate, for evolution and sort of reproductive isolation, which leads to new species. But now we talk about what the value of biodiversity is. The Gaia hypothesis by James Lovelock and Lynn Margulis stated that that life itself can control the environment. With experiments manipulating the number of species, such as in grasslands, where they could manipulate grass seeds, they found that the species diversity did have an impact. It wasn't always a strong linear impact, but it was. And there were similar examples with animals, such as with dung beetles, and where they found that with the increasing number of species present in a site, that dung removal would increase with quite a strong relationship. It wasn't as clear cut in Scottish mudflats with invertebrates. Some of good work by David Raffaelli and Martin Solon, and I was fortunate to be an undergraduate there to help them with their research. And they measured the nutrient flux from the sediments, and it wasn't always a strong relationship, but it was a stronger relationship with functional groups. So a strong digger, bioturbator, with not a very strong one, more grazer, with a filter feeding bivalve. This research can translate into understanding of ecosystem services, which are the goods provided from ecosystems based on its biodiversity to human society. This can include pollination, recreation, artistic influence, but then again there are also ecosystem services such as venomous snakes. Those are my hands after meeting that snake, and there are of course insect-borne diseases too. But it depends. At the end of the day, it depends on the biodiversity present. And here is an example of filter feeding bivalve mollusks, in this case oysters. Here cleaning out the water, and it's estimated that oysters particularly can filter out a lot of pollutants from water, and this is why there's many projects now trying to restore them. And while oysters might be reintroduced to the likes of New York or London's estuaries, wolves have been reintroduced to Yellowstone, where it was found that they regulated elk populations, which then regulated riparian tree communities, which then impacted riparian passerine birds and beavers. But finishing up on a cultural ecosystem service now, I show this mural I saw last week in Brighton, and it was of a sea dragon, and it was just more an artistic. It was a very pleasant example where someone was talking about how to go flow with the ebb of the currents like a sea dragon, and it makes me remember what David Attenborough said, that of all these 8.7 million species, these are 8.7 million solutions on how to survive. So I'll leave you with some recommended reading. If you want to start with more accessible literature, I'll introduce you to Edward O. Wilson's Diversity of Life, and also David Quammen's Song of the Dodo, which I actually prefer. There's also more technical papers for you to go through if you find them useful. Okay, thank you.